Welcome back to ECE 442-542. The next time we see each other will be exam day. Exam number 2 is Wednesday. Homework number 4 is due this evening, and we have an exam review session tonight, and that's in a different location, so we will have to close up and reopen after this class, which this class ends in about 75 minutes. Today what I want to do, and there will not be any office hours the Friday before spring break. We don't have class that day. I hope you're not planning to come see me on that Friday. I won't be around, but if you need to see me, send me an email and we can try to arrange some time that's not after Wednesday, because I won't be here after Wednesday. I'll be here for the exam. Today what I want to do is quickly talk about the process for exam number 2. It's consistent with the previous exam, and we will then get into how do we realize a difference equation or a discrete time realization of a low-pass filter based on the pole zero matching approach. And we will try to illustrate why MATLAB might be giving you something different from what you did in your derivation when you do the matching technique. And in particular, it is, why is MATLAB only mapping 1 0 at infinity, and you told us to map 2? So we'll talk about that, I hope, in this implementation issue, and I hope that now it will make some sense as to why we're talking about that now that you've identified this difference between maybe what you did by hand and what MATLAB was giving you with the C to D function. And that will then really be the material that you'll be responsible for on the exam, and then we will start new material. So today's material will fill in some gaps, maybe you don't have any gaps, but the first 2 topics will be valid material for exam number 2. For exam number 2, the blues are allowed, the reds are not allowed. The blues, you can have 2 sheets of notes and a Z-transform table. That Z-transform table can be either the one that you used for exam 1 or the one that's now been posted for exam 2. It's different, but I will allow whichever one or one that you prefer. Just bring one. You can have a calculator and something to write with, but then don't be talking or looking around. I tried to separate you, and that wasn't even quite enough. Don't share calculators, because we could have answers being on calculators when you pick up your neighbor's calculator. You don't want to get the wrong answer. No textbook, no course notes, and no computer. Any questions on the process for exam number 2? Yes. Yes, did I not show that? The notes are FRT and BCK, so you can have basically four sides of notes, just 2 pages. Is that okay? So you're allowed 2 sheets, but those sheets can be covered front and back. Does that answer the question that was raised? Let's quickly go through this pole zero mapping that we have talked about and you've now had to work through on homework number 4. And this is really using this relationship or this mapping of z is equal to e to the st. The first thing you do is you factor your analog transfer function, capital H of s. And when would you use this versus maybe a 0 order hold? This is a discrete equivalent. we have many different ways of performing a discrete equivalent, and they have two different scenarios. We've lumped this discrete equivalent into what scenario? Scenario 1 or scenario 2? And it's not important the number of those scenarios, it's just that we've associated these into sort of classes. Does this discrete equivalent fall into the same category or scenario or class as thumbs up, zero order hold, or thumbs down, the numerical integration discrete equivalents? Is it clear what I'm wanting you to answer? Either up or down. Does this pole zero mapping, and I think I've already answered the question, didn't I? Maybe, if you were listening. I don't know. I may be sleeping. I feel like I did the hackathon and I didn't do the hackathon. Thumbs up if you think this pole zero mapping is consistent with, and don't show me your thumb yet. I don't want anybody to give away the answer. Thumbs up if it's consistent with or it belongs in the same scenario or class as zero order hold discrete equivalent, or thumbs down if it belongs in the same class as our numerical integration approaches. And those are forward, backward, and trapezoid, are the three that we went through. On count of three, I want to see a thumb up or down, or I guess sideways. Sideways is if you can't decide. 1, 2, 3. Most are showing me a downward pointing thumb, which is correct. This is now a discrete equivalent that you might want to do if you are transferring a filter from continuous to discrete, or a controller from continuous to discrete. The zero order hold is usually used when you're trying to convert a plant or a system that's preceded by a zero order hold. And you're trying to lump those two pieces, the zero order hold and the system dynamics, into one transfer function. All right, so we first factor h of s, then we map the poles and the zeros through this mapping. Z is equal to e to the st, and we produce pole factors and zero factors for our finite zeros in h of z. Then up to this point, we've said if you have infinite zeros, which are equal to the number, or the pole zero excess, if you have 3 more poles than you have zeros, then you have 3 infinite zeros. You map all of those into this z plus, or that number of z plus 1 factors. You would have a z plus 1 to the third. That's what we've talked about, and we'll talk about how we could maybe change that and why we might change that. And then we match the gains of h of s with h of z. And I can't tell you what s and z to use until you sort of know what your h of s represents. Do you understand what I'm meaning by that? If your h of s is a low-pass filter, what value of s do you want to match with what value of z? And now you could show me symbols, couldn't you? You could say 0 is S and 1 is Z. You want to map DC if it's low pass in behavior. You're looking at matching the low frequency. If it's a high pass behavior, then you might be looking at S going to infinity for H of S and Z going to -1. And if it's something else, if it's, you don't know whether it's band low pass or high pass, if it's band reject or band pass, you could match whatever frequency you want, and you could just use that relationship Z is equal to e to the st to make that matching of gains. We've looked at the pole, or the low pass filter variety of this pole zero matching. We have 1, 0 at infinity because of the pole zero excess being equal to 1. We have a pole at -a, and we have a DC gain of 1. That then maps, or according to MATLAB, is matched. That's just M-A-T-C-H. There's no .com after that match. Sorry, you guys, never mind. So you're matching or mapping, that's the same thing. And this is what I think we derived last time. And that z plus 1 factor is because we have 1 0 at infinity, is what we've talked about. And our pole is located consistent with our pole in the s-plane. It's at z equal to e to the minus at. That's the value of z that will cause that denominator to vanish. The z value that causes the numerator or the whole thing to collapse to 0 is a value of z equal to minus 1. And if you set z equal to 1, you should end up with a g sub d of z equal to 1 equal to 1. And that's matching the gains at low frequencies. Now that we have that, let's try to generate a difference equation that will implement this filter. That's in the frequency domain. We now want to generate something that we can number crunch on with a computer. Somebody gives us a string of data and they want it low pass filtered. You can now do this difference equation in order to low pass filter the signal that you're given, this string of numbers that you're given. You are taking this string of numbers, we'll call it E's, and produce an output sequence that's now the low pass filtered version of that input sequence. To do that, we now need to go from the frequency domain into the time domain. If we are starting with where we left off, we have our g sub d of z. That's our transfer function, and that's this ratio of our output of the filter to the input of the filter, where the output of this filter we're designating as u, and the input is e. We derived that that's 1 minus e to the minus at. That's just a numerical value once you know the sampling period capital T and the pole location A. That was over 2 times z plus 1 over z minus e to the minus at. And if we're wanting to actually take that into the time domain, sometimes it's easier to work with delays versus advances. And since this is only first order because the denominator has a polynomial factor in z to the 1, we could actually scale this by 1 and then produce a ratio of polynomials in terms of z to the minus 1, which will be nice when we go into the time domain. Those will correspond to delays of some amount, which in this case will have delays of nothing and delays of 1. When we end up with this relationship, we now have u of z over e of z equaling 1 minus e to the minus at over 2 times 1 plus z to the minus 1 over 1 minus e to the minus at z to the minus 1, just distributing that z to the minus 1 through. If we now cross multiply, and let's just keep this messy piece together, that's just a number with a and t, so don't get too worked up about what I've indicated in red. That's just some number. We'll keep that together, multiply both sides through by the denominator factor and capital E, and put it into the time domain, and we end up with, I hope, the same equation. we have U of n, let's say on the left, and I'll put everything else on the right. We also have another U in that expression, but it's been delayed by one time step. Here I'm basically not explicitly including the sample period capital T in the argument. I'm just saying this is index number n for U of n. But now on the right-hand side, we have e to the minus at U of n minus 1. And that's really just coming from that piece just slid over to the right-hand side after multiplying through and adding. I hope that's okay. And then we have the other piece, which is our gain. That will be weighting e of n and e of n minus 1. And what I'm wanting to do now is pay close attention to the arguments of these time domain waveforms. Our output is u, the input is n. We actually have little n on the left. This is the output, and this may seem pretty trivial, but I want to make the point. This is the output at time little n, or you could think of that as now. This particular term on the right-hand side, the first term, is the output at time n minus 1, which is one time step before now. And the two inputs in the blue bracketed term, here is our input at time n, which is now, and this is our input at time little n minus 1. Which is really saying this string of numbers, the input string that's coming in, we have to process two of those to generate the next output, which is u, but we actually are generating the now output using the now input. Those are theoretically, according to this difference equation, at the same time instant. And you may not have that available to you. That's what I'm wanting to try to make clear now. Is this expression clear? And just think you have this string of numbers e coming through. You can now multiply the sum of e now and e one time step before, scale that by red, and add that to the output one time step before, and now you have the signal of the output now. And you just keep doing that. You'll have to have some storage, some memory locations, but that's can be done. You just pull up those particular values, add them together, scale it, and add them to the previous output and generate the current output. And that's low-pass filtering this signal that's coming in at E. There may be some issues when you go to implement that low-pass filter. And these implementation issues can be resolved or cleaned up by playing with the zeros at infinity. And that's what I'm trying to indicate here. The zeros at infinity, and when the input waveform is actually available. Which maybe instead of somebody handing you this long data string, maybe you're sitting there waiting for the next input. And you can't do anything until you get the current input. Then you quickly multiply things together and spit out the output. And you'll have to do some crunching before you can spit out that U. Meaning you could, if you're waiting for the next, or if you're waiting for now and it's just been a little bit later or a little bit earlier, guess I'm hungry, I'm thinking of now and later, it's now and earlier. So it's earlier, you have just generated U at time n minus 1. You could, before it becomes one more time step, maybe in your processor, you could compute that red gain times E, add it to e to the minus at times U of n minus 1, but then you have to wait until you get the input now, scale that by the red, and add it to that last sum that you just generated to produce the now output. And how long that takes may be an issue. If it happens really, really quick, and what do I mean by really, really quick? If that takes less than 10% of your sample period, you're probably okay. That's another one of these rule of thumbs. But if it's taking long, if it takes half of your sample period to multiply or scale that existing input, add it to the sum and spit out the output, you may have trouble if you're trying to use this in some control environment. If you're doing it offline, it probably doesn't matter. This is what I want to make clear. If the input at the present time, and the present time is t is equal to n capital T, and now I'm putting the capital T in there. Don't ask me why, but sometimes I put it in and sometimes I don't, and I hope you understand that that's okay. You just have to always assume that you're so many sample periods into time. If the input at the present time is not available, in the implementation of the digital system, meaning you don't want to wait and do this processing after you've now captured the input at the present time, and you want to, when now hits, you want to quickly just spit out the output, then we want there to be a one sample period delay between all of the inputs and the output, at least a one sample period delay. So if the input is not at the present time is not available, then one of the zeros at infinity needs to actually be mapped to infinity and not this factor z plus 1. Needs to be mapped to z equal infinity. I can try to say that another way. That is, only map, and here you have to try to keep track of my brackets and curly brackets and parentheses, you can compute the number of zeros at infinity. In your homework, how many was that? Did we only have one of these problems where you had to use the pole zero mapping? Or did we have more than one? Just one? And how many zeros at infinity did you have? 2, didn't you? You had a pole zero excess of 2. So this number in parentheses, this number of zeros at infinity is 2. What I'm saying, if the input is not available at the present time, then reduce that by 1 and only map that number in curly braces to the location z equal minus 1, or only include one of these z plus 1 factors in g sub d of z. And for those of you that have already played along, this is actually what's happening in MATLAB. They are preserving a one sample period delay, or they're fixing at least 1 0 at infinity in their matched approach. This is, I'll say, the MATLAB approach. Let's see what that means relative to the example that we just looked at. Here was our g sub c of s. That was a over s plus a. We want to produce a new discrete equivalent. And since it's new, I will put a bar over it. It's not the same as g sub d of z. Before, so I'll unbar it for just a minute. Sorry if you're taking notes in pen, but don't erase it. I'm going to add it back in just a minute. This is what we had before. Now what we want to do is we actually want to eliminate that factor, because we had 1 0 at infinity, and we said let's map 1 minus 1 of those into this factor z plus 1. Now we have a factor z plus 1 raised to the 0th power, or it now gets eliminated. So we're going to remove this factor, or remove 1 0 at infinity. And we've actually put, so this is, you kind of have to, I guess, know what I'm meaning by my zeros at infinity. Now we've put 1 0 at infinity. Now z going to infinity will cause g sub d bar to vanish, or to equal 0, with this modification. This is different than what we had before, and this will obviously, I hope, give us a different difference equation. And the difference is going to show up in the number of terms on the right-hand side, and possibly the value of k bar. We can now find k bar again by matching gains, and the matching gains, this was low frequency and behavior. We now want to match g sub d of z bar at z equal to 1 with g sub c of s when s is equal to 0. We do not have that z plus 1 factor in the numerator, which means that we only have k bar. Downstairs we have 1 minus e to the minus at. And on the right-hand side, we have g sub c of 0, which is a over a, or 1. And this now gives rise, or allows us to conclude that k bar now is 1 minus e to the minus at. Or our discrete time transfer function is now 1 minus e to the minus at, 1 over z minus e to the minus at. And if we want to look at what the difference equation looks like associated with this g sub d bar, we can again convert it to be made up of delays instead of advanced operators. And we now have 1 minus e to the minus at, z to the minus 1. Again, that 1 minus e to the minus at is just a numerical value. And downstairs we have 1 minus e to the minus at, z to the minus 1. And now if we take this into the time domain, by cross-multiplying and realizing that z to the minus 1 is a delay in the time domain, we end up with u of n equaling e to the minus at u of n minus 1 plus 1 minus e to the minus at u of n minus 1. Told you I was feeling like I was at the hackathon, half asleep. E to the n minus 1. Do you see that this does differ from the previous implementation of our low-pass filter, which was right here? And to maybe see the difference, I would take that 2 that's in the denominator in the red box and slide it underneath the e to the n and the e to the n minus 1. In the blue box here, you're basically averaging the input now and the input one time step before and scaling it by 1 minus e to the minus at. In this modified version, where we do not have the input at the current time, we're not doing any averaging. We're just taking that input and scaling it by the same factor. We're not averaging it with previous or current values of the input. But this again will what? It weights the previous output by that same factor, e to the minus at, and it scales the input one time step into the past by this same factor, 1 minus e to the minus at, which this result is averaging the input now and the input one time step before. Yes? There aren't any zeros at infinity. Now you're saying, well, let me see what you are saying. If you have a high-pass filter, maybe, then you might have equal numerator and order as denominator order, and then it now where was I? So you may have to then, let me see. I'm not sure that you would want to do anything. You might have to, though, go back and see if there's a way that you could do something similar to what we did by forcing a 0 at infinity if you needed to make this one time step delay. Here it's natural to do. You can simply use this approach, if you do have zeros at infinity, then you can simply reduce that number by 1, and then that's preserving this one time step delay between the input and the output. Yes? So will this preserve stability? So the question was, does this preserve stability? What influences stability? The poles. Have we changed the poles? We haven't changed the poles, so we're okay with respect to stability. That's a reasonable answer because we're messing with things, aren't we? Or I'm sorry, that's a reasonable question. We're messing with things, but is that influencing stability? No, it's not influencing stability. We are changing the zero structure, and the zero structure in the time domain we've learned, or in continuous time systems, usually shapes the output response. So we may be shaping the output response between the first difference equation implementation and the second, and obviously we are. Because in the one, we are maybe using a little bit more information each time we generate an output. We're using 2 inputs versus the previous, or the second one, which we're just using 1 input to generate the next output. That influences the transient shape, but it doesn't influence or impact the stability nature of the design or of the system. Other questions on this material? Is it clear now the difference between what you were doing by hand and what MATLAB was giving you if you've done your homework? And you could make yours agree with MATLAB by saying, I'm going to force a 1 sample period delay between my input and the output, and then your work, your hand work, you would just have one of those z+1 factors. You would use that to establish your gain, and then your work should be consistent with what MATLAB was producing. Questions on that? Can we draw a line in the sand or on the tablet? There is our line. That's now exam number 2. Don't fall asleep on me. I can be the only one falling asleep. Let's move on to material that we will be doing for exam number 3. Wow. We have exam number 3. We have the final exam, and somewhere in there you're going to have a project. I'm going to try to give you the project description. I'm holding off because we don't have everything that I want you to be thinking about for your project. So we're getting now into the control aspect. We've been doing a lot of modeling and filtering, discrete equivalence. Now we want to be thinking about how do we reshape or how do we establish the desired closed-loop poles in the z-plane like we were comfortable with, maybe, if you've had an earlier class, the S-plane pole locations in an analog control class. If you haven't seen that, we'll try to make the connection now. And this is relating time domain behavior with frequency domain pole locations. And we'll do these poles in the frequency domain, in the S-plane and the Z-plane, based on a pure 2-pole system. And pure means the ivory soap version, 99.9% pure. No, it means we don't have any finite zeros in the S domain, G of S. If it's a pure 2-pole system, we don't have a zero floating around. That's what we're using or assuming to derive these relationships between time domain values and frequency domain pole locations. Let's look then at what we'll call design specifications and second order pole locations. Let's start, this is maybe easier to think about in the continuous time case, and then we know how to map. We've talked about mapping between the S domain and the Z domain. Let's look at an underdamped second order system associated with a continuous time system, and we're looking at this system in the frequency domain. So that now we could write that as our natural frequency squared over a denominator that's S squared plus 2, that's a zeta, omega sub n s plus omega sub n squared. We might write it that way, or we might write it as sigma squared plus omega sub d squared all over S plus sigma squared plus omega sub d squared, where all of these sigmas, omega sub n, zeta, omega sub d are associated with distances or values in the S-plane. This is now the S-plane. We have our damped frequency omega sub d, and that's really the imaginary part of your complex pole pair. Omega sub d is the natural frequency omega sub n times the square root of 1 minus zeta squared. And now I have to try to draw a circle, just 1/4 of a circle. And suppose that we now have a pole right there, and we have its twin down in the third quadrant. This particular pole has a real part that's a distance sigma into the left half plane, where sigma is now zeta omega sub n. This distance away from the origin, that's supposed to be a hypotenuse or a straight line, that is omega sub n. The angle that that hypotenuse makes with the negative real axis we will call theta, and don't confuse that with theta sub d. It's a different angle. This is in the S-plane. And the vertical or imaginary component of that pole is a value of omega sub d. This pole S is at minus sigma plus j omega sub d, and we are going to relate those sigmas, omega sub d's, and zeta. Zeta I haven't really indicated here, but zeta is related to theta, where if zeta was actually equal to 1, that pole would have swung all the way down and theta would have been 0. If zeta was actually equal to 0, then now we have a purely imaginary pole. That blue X is now rotated up. If we let zeta equal 0, our relationship between omega sub d and omega sub n, they become equal. the natural frequency, the distance away from the origin, is the same when zeta is equal to 0. Omega sub d and omega sub n become the same. Now, all of these relationships are captured, or those are actually the pole locations in our transfer function g. If you now found the roots of your denominator, you would have one root at minus sigma plus j omega sub d and its twin, s equal minus sigma minus j omega sub d, and that's on the right-hand side of that expression for g of s. The other one is in terms of zeta and omega sub n, or this angle and radial distance away from the origin. So you're sort of comparing or using either rectangular form for your pole location or polar notation for your pole location. Meaning the poles are at, let's say the one that I've indicated is at minus sigma plus j omega sub d, but sigma is actually just minus zeta omega sub n. That's the real distance into the complex S-plane, plus j omega sub n square root of 1 minus zeta squared. And some of the terminology that we will use, this sigma value, we will refer to that as the damping in our system due to those pole locations. Zeta itself, which varies between 0 and 1 for an underdamped system, is our damping ratio. Omega sub n is our natural frequency. And omega sub d, which is the square root, or omega sub n times the square root of 1 minus zeta squared, is our damped frequency. And if you wanted to, what happened to my theta? It lost its bottom. If you wanted to look at what that angle is, theta, you could relate theta, zeta, and omega sub n if you said, well, I'm interested in the cosine of that angle theta. That's now the adjacent sigma over the hypotenuse. But sigma is just zeta omega sub n. So zeta is now equal to the cosine of theta, or if you wanted to, well, if you measured that angle theta, you could then compute your damping ratio, or if you wanted, if you had zeta, you could find theta by doing the inverse cosine of zeta. And that's now how these are all interrelated. That being given, let's now look at some of these time domain properties or transient response characteristics relative to these pole locations in the complex S-plane. If we were to generate a step response for an underdamped system, it might look like that. It's going to go up and bang around a little bit. Let's say that this is now y of t, and if I could, which I probably won't be able to, just humor me and assume that that's where we finally go with our output y. That's the final value of y. we might actually be interested in when that, so this is why you have to humor me. We will, in this class, worry about when that particular response of our step response gets inside and never leaves a 1% tube, meaning we look at our final value and we take 1% of that and we go up and down 1% around that final value, and we say, at what time does that blue line or our step response get into that 1% tube and stay there? That's the time that we will call our settling time T settle. That's our 1% settling time. We can also identify this point, which is, we will label it as y T sub p. This is our peak time T sub p. We've now, what are we doing? We have a system. It's a second order system, and we now hit it with a step input. If we hit it with a step input, it will generate this step response, and once we have this step response, we can now identify all of these points. We can identify where it finally goes to, its final value. We can identify when it gets within 1% of that final value and never leaves. That will be our 1% settling time. That's capital T subset. We can identify the value where it reaches its maximum. That's y of T sub p, and we can identify when it reaches y of T sub p, and that's our peak time, T sub p. And now with those, we can relate those, because these are characteristics we might be interested in terms of performance of our system. We might not be happy with the way the system naturally is settling. We may want to speed up the settling time with a controller. We may want to reduce T set. We may want to reduce time to peak. We may not like how big y of T sub p is. That's our percent. That's going to influence our percent overshoot. These are all transient behaviors that we may want to shape or select, or our boss might actually want us to produce or achieve with the system that we're working with. Let's now try to relate these transient behaviors or variables with the sigmas, the omega sub d's, these pole locations in the S-plane. Y of t, that's our step response, is by definition the inverse Laplace transform of capital Y of S. And that's just the inverse Laplace transform of our second order system, our pure second order system. And now I am using U of S as an input. So U of S is our input, or the Laplace transform of our input. If we wanted to find Y, the output Y, when we reach the peak, what kind of calculus thinking would we be using? If we want to know, how do I find when we reach Y at the peak, or when Y reaches its peak, what kind of a operation, hint hint, calculus operation, might we use on Y to identify when, or the value of time t when we peak? We want to look at the derivative of y, and when that reaches 0, we've reached our maximum, and we're really wanting that the first time after t equals 0. We have a lot of maximums or relative maximums in this step response. We want the first one. That's our time to peak. This is now saying we want d by dt, and we want to set that equal to 0. And the first time that that occurs at the particular point of time, that will be our time to peak. Well, we've been making a big deal about playing in the frequency domain. If we now have y prime of t, that's now the inverse Laplace transform of the derivative of the output, but the derivative in the frequency domain is s times y of s. Now if we have s and we had g of s, which was this omega sub n squared over s squared, boy, I'm going to have time. Let me write it a different way so I don't have to squeeze quite so much in. We now have s plus sigma squared plus omega sub d squared. That was our g of s. Suppose we just use a unit step. This is now our unit step in the frequency domain. And that's now what we have, but if we want the derivative, those s's cancel. And what do we have when we inverse Laplace transform that expression on the right in the square brackets? Or what kind of a shape do we have? We have poles that are complex conjugates. And what kind of a numerator do we have? Constant, or does it have a zero factor? It's constant, which if you go into the Laplace transform tables, you'll see that this corresponds to, you're either dealing with an exponentially damped cosine or an exponentially damped sine because of the complex poles and the fact that we have a sigma. That puts us into the negative left half s plane, so we have an e to the minus sigma t, cosine omega sub dt or sine omega sub dt, and we could have had a combination of those if we had a s in the numerator or a linear factor in the numerator. We don't have that. We just have a constant, and this would be a lot easier if the numerator was actually omega sub d. So let's force it to have an omega sub d by multiplying by 1. And factor out what we don't want in there, and that will just be a scaling factor. If you look in your tables, you'll have omega sub d over s plus sigma squared plus omega sub d squared. That is, in fact, this exponentially damped sine wave. And we've now just scaled it by omega sub n squared over omega sub d, meaning this is now omega sub n squared over omega sub d, e to the minus sigma t sine omega sub d t. That's the derivative of our output of this unit step response. Let's remind ourselves of what we're trying to do. We want to find when that reaches a maximum, or when y reaches a maximum, for the first time after t equals 0. And we've now found an expression for the derivative of y. We now want to look at the first time after t equals 0 that y prime of t in fact equals 0. When will that happen? When will that right-hand side in red first become equal to 0 after t equals 0? Is it clear at t equals 0 what that's going to be equal to? When you plug in t equal to 0, you have e to the 0, 1, sine of 0. Sine of 0 is 0, so that's going to be 0. We don't care. We want to know when is the next time that expression equals 0 for t. We need to focus on the sine piece, don't we? That e piece is irrelevant. So now we need to say, oh, that will become equal to 0 when we have the sine of omega sub dt equaling 0. And that occurs when omega sub dt, or the argument, is equal to pi. And that's going to, so this, let me change my t to actually be t sub p when this occurs. And now we can solve that for when we peak, which is now this pi over omega sub d. So if you know where the poles are located and you actually know the imaginary component of your two complex poles, you can now immediately tell me when it's going to peak. It's going to peak Saturday divided by omega sub d. At when? 6:29 in the morning. 9:26, if you're in on the joke. 3.14, March 14th, that's pi day. But we have pi over omega sub d. I had a student in a class, we usually teach 442 in the spring, so we always have a pi day in this semester. And he said, Dr. Tharp, I got married on pi day. And he goes, at 1:59 p.m. So 314159. I go, wow, your wife allowed that? And I'm working on down a little bit later, and I go, I'll be darned. I was married on 2 pi day. And my wife had nothing to do with it. Neither did I, but I can remember my anniversary that way. Not that that's why I did it, but I could really turn nerdy, huh? So now if you're given your poles, you know what your peak time is. If you're given your peak time, if somebody says, I want a peak time of a certain amount, now you know what omega sub d needs to be, or what your imaginary part of your two closed loop poles need to be. And again, these are all just rules of thumb based on a pure two-pole system. If somebody says, I want a peak time of 0.5, now you know what omega sub d has to be, or at least if you can tolerate a peak time less than 0.5. Is that clear? You can now translate a particular design spec into an imaginary component of your closed loop poles. And those may not be what your open loop system is producing. Let's look at a different time domain property, PO. Post office, no. Percent overshoot, not post office box. This is now y of time to peak minus y final value over y final value times 100%. Can I let you in on a secret? No more anniversaries or dates, but a lot of students seem to not put the final value in the denominator. They seem to put y time to peak. Remember this relationship. It's the difference between the peak and the final value divided by where you eventually end up, which is the final value. And that gives you your percent overshoot. You could compute that if you know your peak value and your final value. You can now specify what the percent overshoot is. And you can also relate that percent overshoot to pole locations. If you go through the manipulations, you'll find that the percent overshoot is actually e to the minus, zeta is the damping ratio, pi over square root of 1 minus zeta squared. You can show that relationship to be true. And this now allows you to solve for the damping ratio, which says if somebody gives you a particular percent overshoot, you can tell them what your damping ratio needs to be to accomplish that percent overshoot. And you can derive this. You might want to do this on Pi Day. Since this won't be on exam number 2, you don't have to do it before Wednesday necessarily to derive this, but there's pi squared in the denominator, and what's that roughly? Pi squared. 10, that's rough, okay? So pi squared is roughly 10 if you're on Jeopardy and they ask that. I don't think they've ever asked that on Jeopardy. But maybe you could outsmart Deep Blue. Because they might say pi squared. What is 10? Right? Approximately. Maybe you want to put that approximately in there. This now relationship between percent overshoot and zeta, you could actually sketch, and it has a nice shape to it, and you can actually identify certain values of zeta. Zeta of 0.7, here's the zeta axis, and let's say this is our percent overshoot axis. For those of you that had the earlier class, a zeta value of 0.7 corresponds to what percent overshoot? Do you remember? It's approximately 5%. Then if you looked at a zeta value of 0.6, that's approximately, I'm going to go a different color, 10%. And if you had a zeta value of 0.2, that's going to give you a pretty big overshoot, which is 50%. Which now somebody might give you a specific percent overshoot and say, I want a percent overshoot of 10% or less. That says your zeta value needs to be 0.6 or larger. What's the angle associated with a zeta value of 0.7? We know that cosine of theta is, well, we could do adjacent over hypotenuse, which was zeta omega sub n over omega sub n, just to remind ourselves. That was zeta. Now we could do theta is equal to the inverse cosine of of zeta. And if zeta is 0.7, what's the angle? You don't have your inverse cosine table mentally memorized. This is an angle of 45 degrees. That's a sweet spot, approximately 45 degrees. So if you are asked, again, maybe on Jeopardy, what's a nice distribution or location for your closed loop poles, you might say, oh, it's nice to have the real part and the imaginary part the same, or to have an angle of 45 degrees. And you want to move out far enough into the left half plane to achieve the settling time and the peak time that you might need. Let's now relate that. So now we have percent overshoot and peak time. Let's look at one more, which is settling time, transient behavior. we have e to the minus sigma t is now our response behavior in the damping portion, or you might see that as e to the minus t over tau, where tau is the reciprocal of sigma. And if we wanted, now we're saying our settling time t is roughly 5 time constants, where tau is a time constant. This is now then if we were looking at a 1% being 5 time constants, that says that, well, the reason we say that is if we looked at e to the minus 5 tau over tau, that's now e to the minus 5, and do you have your exponential table burned into memory? What's e to the minus 5? A very small number. It's less than 0.01, and we just approximate it to be 0.01, which is our 1% of where we started. That's where that 1% settling time is coming from in 5 time constants relationship. So if we say we want a 1% settling time, we're approximating that by 5 time constants, then we have t settle is 5 tau, but tau is reciprocally related to sigma, which is the distance into the left half plane. This is now 5 over sigma, or that's now 5 over zeta omega sub n. Which means that if you want to reduce your settling time, where do you want to put your poles in the S-plane? Closer to the imaginary axis or further away? Based on sigma and zeta omega sub n. Now let's go back to wherever we were, here. And if we want to reduce our settling time, T settle is 5 over sigma, wasn't it? Wow. 5 over sigma. If we want to make T settle smaller, we want sigma bigger, which says move further into the left half plane. We have a larger numerical value for minus sigma. We have e to the minus something. Let's see what that means then. I just told you what that looks like in the S-plane, but we can now start translating those design specifications into corresponding behaviors or properties in the complex S-plane. For example, our settling time is now 5 over sigma, or we could say that sigma is 5 over T settle. Sigma 1 versus sigma sub 2, if we want to decrease T settle, is it clear that we want to move from blue to red from that relationship of T settle and sigma? So now if somebody gives us a T settle, we can figure out what our sigma is. If somebody knows where our closed loop poles are, we can figure out what T settle is from sigma. And we will show similar relationships. Actually, the percent overshoot is influenced by the angle of that line of theta. and the peak time is influenced by how much imaginary component we have in omega sub d. We'll pick up at that point, wow, after spring break, if you can remember that. But the next time we meet, which is Wednesday, will be exam 2, unless you're going to the review session, which is in 15 minutes.